Right now, your phone knows exactly where you are, not your street or your neighborhood, your exact location within a few meters, anywhere on Earth, and it figured that out using signals from satellites floating 20,000 kilometers above your head. So how does that actually work? To understand GPS, you first need to picture what's happening above your head right now. There are 31 active GPS satellites orbiting Earth, and they aren't randomly scattered. They're arranged deliberately so that at any point on the planet, at any time of day, you can see at least 4 of them in the sky above you. Each one is moving at about 14,000 kilometers per hour, completing 2 full orbits around Earth every single day. And inside every single satellite is something extraordinary, an atomic clock. These clocks are so precise they would only lose 1 second in a million years. That level of accuracy isn't just impressive trivia, it's the entire foundation GPS is built on. Without it, the whole system falls apart. Every satellite is doing one simple job, broadcasting a radio signal out into space. That signal carries just 2 pieces of information, right? Which satellite this is and what time it is right now down to the nanosecond. That's it. It repeats that over and over endlessly in every direction, whether anyone is listening or not. Most of the time, nobody is. But when your phone picks it up, the real work begins. When your receiver catches that signal, the first thing it does is measure time. Very, very carefully. The signal travels at the speed of light, roughly 300,000 kilometers per second. Your phone knows the exact moment the signal was sent because the satellite stamped that timestamp right into the broadcast. It then checks the moment the signal actually arrived. The gap between those 2 numbers tells it how long the signal was traveling. Speed multiplied by time equals distance. That's the whole formula. If the signal took 0.07 seconds to arrive, your phone calculates the satellite is roughly 21,000 kilometers away. But here's the catch. Knowing you're 21,000 kilometers from one satellite doesn't tell you where you are on Earth. It just tells you that you're somewhere on a massive invisible sphere surrounding that satellite. You could be on the ground, underwater, in the air, anywhere on that sphere, so you need more. A second satellite gives you a second sphere, and those 2 spheres overlap in a circle. You're somewhere on that circle. A third satellite gives you a third sphere, and 3 spheres intersect at exactly 2 points. One of those points is usually somewhere physically absurd, like 50,000 meters above the Pacific Ocean, so your receiver automatically picks the logical one. 3 satellites technically gives you a 2D position, latitude and longitude. Good enough to put a dot on a map, but for true 3D accuracy, including your precise altitude, you need a 4th satellite. And the reason for that goes much deeper than just altitude. Here's where most explanations stop, and where GPS gets genuinely fascinating. Those satellites carry atomic clocks worth hundreds of thousands of dollars. Your phone does not. Your phone has a cheap quartz clock, the same kind inside a basic digital watch, and that gap in quality is a serious problem because even a clock error of just 1 microsecond, 1/1,000,000th of a single second translates into a position error of 300 meters. That's the distance between 2 cities. So how does a cheap phone clock give you accuracy down to a few meters? It cheats, and it cheats brilliantly. Your phone doesn't trust its own clock. Instead of assuming the clock is right, it treats the clock error as just another unknown variable to be solved, the same way you'd solve for x in an algebra equation. Think about it this way. You have 4 unknowns: your position in 3 dimensions, latitude, longitude, altitude, and your clock error. 4 unknowns need 4 equations to solve. 4 satellites give you exactly 4 equations. Your phone runs all of them simultaneously and solves the entire system at once, finding not just where you are, but also exactly how wrong its own clock is and then correcting for it in real time, silently, every single second. This is why GPS is also one of the most precise timekeeping tools on Earth. Banks use GPS timestamps to synchronize financial transactions across global servers. Power grids use it to coordinate electricity flow across thousands of kilometers. The backbone of the internet relies on it to keep data centers in sync. Your phone is quietly recalibrating its own clock every moment, just by listening to satellites overhead, and you've never once had to think about it. Now that you understand how the system works when everything goes right, it's worth understanding why it sometimes doesn't, because you've definitely opened Google Maps and watched the blue dot put you 2 blocks from where you actually are. The first issue is the atmosphere. GPS signals have to pass through the ionosphere and troposphere before they reach your phone, and these layers of air slow the signal down and bend its path. Scientists have spent decades building models that predict exactly how much this happens under different conditions, and your receiver applies those corrections automatically. But the atmosphere changes constantly. Weather shifts, solar activity fluctuates, humidity varies, so the correction is never perfectly exact, and a small error always remains. The second problem is multipath error, which hits hardest in cities. When a signal bounces off a glass tower or a concrete building before reaching your phone, your receiver might pick up the same satellite signal twice, once direct, once reflected. The reflected version traveled a longer distance, so it looks like the satellite is farther away than it actually is, which shifts your calculated position. This is exactly why GPS feels sluggish and inaccurate in dense urban environments, but works beautifully in open fields. Third, satellite geometry plays a huge role. If all the satellites you can see are bunched in one part of the sky, your position fix is weak. If they're spread evenly overhead, your fix is sharp. Engineers measure this with something called GDOP, geometric dilution of precision, and it's one of the key reasons modern phones use satellites from multiple countries simultaneously to always keep the geometry as spread out as possible. Even with all these imperfections, consumer GPS today hits 3 to 7 meters of accuracy under normal conditions. Military and survey-grade systems using additional correction signals can get down to the centimeter level, accurate enough to guide autonomous vehicles and measure the movement of tectonic plates. There's one more piece of this puzzle that almost nobody talks about, and without it, GPS would quietly fall apart within a matter of hours. The U.S. Air Force runs a network of ground control stations positioned at specific points around the world: Hawaii, Ascension Island, Diego Garcia, Colorado Springs, and others. Each station sits at a precisely known location and carries its own independent atomic clock. These stations continuously track every satellite in the constellation, comparing what each one says against what physics says it should be saying. If a satellite's clock begins to drift even slightly, a correction signal is uploaded directly to it. If its orbital path deviates from the predicted trajectory, updated data is pushed to bring it back in line. Every single GPS satellite you depend on is being actively monitored, calibrated, and corrected around the clock every single day. Your phone benefits from all of that invisible maintenance without ever knowing it's happening. The last thing worth knowing is that GPS is just one piece of a much larger picture. GPS is American, built by the U.S. Department of Defense starting in the 1970s and opened to civilians in the 1980s. But Russia runs its own system called GLONASS. Europe has Galileo, China operates Beidou, India has Navic, Japan has gnss. Together, these are called gnss, Global Navigation Satellite Systems, and your smartphone uses all of them at the same time. A modern phone can track 30 or more satellites simultaneously from multiple constellations. More satellites means more equations, better geometry, faster position lock, and higher accuracy, especially in difficult environments like city centers or valleys surrounded by hills. When people say GPS, they technically mean only the American system, but what your phone is actually doing is far more powerful than that single name suggests. So here's the full picture. Satellites broadcast their identity and the exact time. Your receiver measures how long those signals take to arrive, converts that into distance, and uses the geometry of multiple satellites to solve for your exact position in 3 dimensions. A fourth satellite lets your phone treat its own clock error as a variable and solve for it in real time. Ground stations around the world keep every satellite precisely calibrated. The atmosphere, signal reflections, and satellite geometry all introduce small errors, but the system is designed at every level to absorb and compensate for them. The result is that you can land in a city you've never visited on the other side of the planet, pull your phone out of your pocket, and know exactly where you are within 5 meters. That's not magic. That's physics, mathematics, and decades of careful engineering running silently in your pocket every second of every day. If this made GPS finally click for you, hit subscribe because many interesting videos are following.